much, everyone. And in a couple of minutes, we are starting this seminar. So thank you very much for your participation, for joining physically, and also for the people online on the Zoom connection. We're really happy to have you here and happy to share with you the content of this seminar. A couple of housekeeping things for me. First of all, I would just kindly ask everyone which is connected just to mute the microphone, and unless there is a question or something, just to avoid listening to unwanted conversation. The second thing is that this meeting has been recorded, so it's actually under recording. So please, if that was probably already expressed in the participation, but please just keep in mind this. If you're not really comfortable with the recording, you may just want to wait in the break for your questions, or otherwise, please go on with the question if you are not worried about the recording. The third thing is that there's no drill for the fire alarm this morning. So if by all means there's a fire alarm ringing, please follow the rules and try to get out of the room in the most possible ordered manners. So thank you for this, for your participation again. EnigmaAI is a seminar unveiling the intelligence behind optimization and machine learning. This is the title of the seminar. Seminar has been kindly supported and sponsored by two of the institutes at the University of Exeter, the Institute for Data Science and Artificial Intelligence and the Global System Institute. We have online here, we're glad to have Professor Mark Kelson and Professor Peter Cox, which are representing the two institutes. And Mark, if you are there, if you would like to give a brief welcome to the audience, that would be fantastic. Thank you.
Fantastic. Thank you very much. It will be very brief, so not to worry, everybody. Welcome, everybody, in person and online. I am Mark Kelson, the Interim Director of IDSAI. We have exciting news about the Institute that will be announced very shortly, so keep your eyes posted for that, developments for the Institute. I'm sure you'll all be interested to hear about our plans. Many thanks to the organizers for hosting this event, to Raphael, Babak, Ramiz, and Milad. This is fantastic. We are absolutely delighted to co-host this event alongside GSI and the Center for Water Systems. Apologies, I can't be there in person. I had planned to be there in person, but I was booked into a meeting during the time I was going to spend commuting into campus, so I just couldn't get there. So we are delighted to see this kind of event happening. This is the type of event that the Institute for Data Science and AI really want to foster, this kind of creative thinking around machine learning and AI. So if you're sitting in the audience and you have a similar idea for some kind of event, this is what the type of activity we really want to see. We want to foster this across the university. It's a huge pleasure to be here. I've had a look at the agenda. There's some very interesting and provocatively titled talks. So I think there'll be some really interesting discussion and hopefully lots of interdisciplinary discussion. So thank you very much for organizing, and I will pass over to Peter.
Thank you, Mark.
Thank you, Mark, and thank you, Babak, and the organizers. Looks like a fantastic meeting. Sorry, I can't be there either. So I'm Peter Cox, the director of the Global Systems Institute at the University of Exeter, and the GSI focuses on issues concerning global climate change and sustainability, prioritizing database assessment of the issues and their potential solutions. And as I'm sure you're all aware, there is a huge and as yet largely untapped potential for machine learning and AI to help us to make better use of data to inform policymakers, the public and businesses. So I'm therefore really delighted that the GSI is able to co-support this workshop alongside Mark's Institute and the globally renowned Centre for Water Systems at Exeter. And I hope you have a great time at the workshop and learn a lot. Thanks very much, Babak. Thanks very much, everyone.
Very much, Peter. Thank you, indeed. Okay, so thank you again, Mark and Peter, for your introduction, and we're going to start our program. You may have seen online the agenda for the day. And there will be a very short introduction on my side. My name is Lele Vinay. I am a senior lecturer in civil engineering. Very little to do with artificial intelligence. Honestly, very little to do with human intelligence as well, probably. But I've been very, very intrigued by the name of this seminar, Enigma, and I tried to make a bit of my homework and try to understand why it's such an enigma. And I kind of related it to the fact that it's something unknown. Enigma is something unknown, and the unknown is always a bit, scary. You're a bit diffident about the unknown. And this track backs from centuries and centuries. We can think of druids and wizards that were making potions that could be able to cure, but also to kill. And people unknown about the nature and the study of the nature that then became science, and the application of the scientific kind of concept that then became technology, found it, initiated this sort of technophobia or science phobia. And this went up on the centuries and exponentially grew with the growth of scientific discoveries and technological progress. And I believe that the epitome of this fear from the people on technology and science is represented by an amazing book written in 1818 by Mary Shelley, which is Frankenstein, where the kind of the creature of a over-ambitious scientist get out of control and became the monster. And this monster went through the centuries, really. So in the 19th and 20th century, this monster changed its shape and its attributes. And we had one of the big monsters actually was the one that was also represented in the big hit movie this summer. I'm not referring to Barbie, if you're asking. It's rather the nuclear power, science, which has like a dreadful impact in terms of the nuclear holocaust, but also the use of nuclear power for energy production has been, in a way, became the boogeyman in many countries in Europe and around the world. And this happened again with nanotechnologies and biotechnologies. And I don't want to mention, the sort of crazy theories from conspiracy lunatics about the nanotechnology, things like that. But the thing is that everything which is unknown always being a matter of fears. And computer didn't escape this kind of trend, if you want. In the essence of computer itself, the etymology of computer is who that computes, who that makes the calculation. And it was very scary at the beginning because this was a human attribute rather than a machine attribute making calculation. And at the moment that, reputed scholars went into this fear and went to this technophobia and went also to describe and to explain that the fact that silicon and carbon are nearby in a way in the periodic table, really reputed scientists from MIT and Stanford, they published papers saying that actually carbon, which is the brick of the life as we know on Earth, and silicon, which is the element for semiconductor and the intelligence, artificial intelligence. I mean, a life based on silicon is not possible on Earth. They say that maybe it is possible, but it could happen in the atmosphere of Venus. So unless you have plans to relocate, there shouldn't be any problem there. But nonetheless, the artificial intelligence attracted a big fear from the public. And if you have something about my age, you can remember movies in the 80s about the Terminator, in the 90s and about the Matrix. And nowadays, I think that the issue and the fear on the artificial intelligence is not that machine will take the world and will exterminate humans, but rather that humans will use artificial intelligence tools to hijack democracy and these kind of things. So personally, I believe that science and technology are developing tools. And then is the way you're using tools that is like positive or beneficial or negative, as long as a hammer, a saw, and a drill are tools. You can use it for building shelters for people in need. You can use it for something else. I don't want to go over there. As the same, artificial intelligence is a tool. So as a researcher, I'm very, very intrigued by the potentiality of artificial intelligence. This summer I was reading about a new system called EnigmaAI, where basically, project manager can upload thousands and thousands of pages related to the, project management of a big project. And then this language assisted system can interrogate the database and providing the answer to question from the people involved in the project, which is very, very interesting. So as a researcher, I'm really, really curious about the potential, the opportunities. As an educator, I'm a bit wary about the use of those technologies from students. I would like to avoid ChatGPT becoming CheatGPT in no time. And as a citizen, of course, I'm concerned that those tools are basically not impacting on the social life, on the democracy, and on our system. So that's why, when coming back to the very beginning, when Babak, Ramis, and Milad came to see me about organizing this meeting, I was very, very keen to offer my support in the organization. As I said, you heard by my bio, I have little to do with artificial intelligence, but I was very keen to support them. All the credits go to them, of course, in the organization of this seminar, by all means. So I'm now really, really curious about what they will tell us about the tools and the use of the tools in our practice, being engineers and being researchers. I'm talking about myself being engineer, being researchers on a wider field, of course. So again, one more time, thank you very much for joining the meeting. Onliners, you are just missing an amazing catering, but we promise the seminar will be as juicy as possible. So thank you very much. And Babak, it's your turn.
Thank you, Lale. Good morning, everybody. I'm really excited to be able to talk to you about very topical, interesting and topical subject. But before doing so, I just want to make sure that everybody can hear me in the back. Right? Cool. What about the stream? Is everything okay? Cool. Awesome. Okay. So today we're going to talk about. Oh, that's a good point. Cool. So today we're going to talk about AI, computational intelligence, artificial intelligence, and all that jazz. And I'm sure most of you could agree that nowadays it has become exceedingly easy to sort of implement these ideas, even if you have listened to a YouTube tutorial about machine learning and that iris dataset, famous iris dataset, and get a result for your dataset. Whether that result is applicable, reliable, that's a whole different story. So nowadays we are sort of overwhelmed with a lot of information and to some extent misinformation. So that was the premise, the idea behind this seminar, to talk about some of this misinformation, some of this mystery surrounding the idea of computational intelligence, artificial intelligence, because it is expected from us, specifically in this room, to be able to distinguish what is promising, what is good, what is okay, what is wrong, what is downright fraud. So on that note, we decided to sort of plan for this event. And to make things a bit easier, we decided to break things down into two separate sections. One gearing toward optimization and how computational intelligence can be used in the context of optimization, which is going to be the first session. Sorry.
Hi, Babak. Sorry to stop you. Just had a message here. Have you shared your screen?
I haven't. Oh, sorry. Okay. That's a good point. Now, what we can do, share screen one. Can they see the screen? Awesome. Now I can't see them, but it's fine. So we were talking about we decided to break these into two separate sessions, one gearing toward optimization. And the second session is going to be about machine learning, which is going to be hosted with my two friends, Ramiz and Milad, which is going to be a really interesting topic, and you don't want to miss that. Cool. Now here's the goal. I can't. Sorry. There you go. So I thought maybe it's not a bad point to talk about myself a bit more. So my name is Babak Zolghadr-Asli. I know it's a difficult name to say. What I do is a joint researcher at Quacks. What is Quacks? A very good question that nobody asked, but I'm going to answer it anyway. So we have at one hand University of Queensland, hence QU at Australia, and then we have University of Exeter, IEX. And then somebody had a very creative day and decided to mash them together to say that this is a joint program between the two institutions. What I do is often described as hydroinformatics, which means that I do deal with hydrology, water engineering, civil engineering, environmental engineering, to some extent climate science, and more importantly, data science and applied mathematics and how they can collide and be used in that context. If you're interested in that sort of topics and you want to stay in touch, you can sort of scan that QR code. It would directly to my personal website. I have a lot of arguably useful information about some Python codings and stuff like this. And you can even find my handles to my social media there as well. So if you want to stay in touch, you can do so. But what about today? What are we going to talk about? Well, in the first hour, we're going to, in the next hour or so, we're going to first understand and provide a bit of a context about optimization and how computational intelligence come into play in that context. Then we're going to understand a bit about the details and the nuances of using computational intelligence in terms of using it for optimization. And if you're lucky, we're going to have a live code demonstration. Worry not, I'm not going to ask anybody to do some coding. I'm just going to demonstrate some code and try to draw some conclusion. And finally, based on the things that we're going to see and discuss, we're going to draw some conclusion about the future of computational intelligence, artificial intelligence in general, and specifically in the context of optimization. Just in case, if you want to read about this, if you miss something, you can refer to this article. It's not necessarily a one-to-one transcript of what I'm going to say, but it's close enough. So if you don't want to tolerate me, that might be a good idea to just scan this QR code and start reading. Cool. So my whole job today is to convince you that there is a connection between these seemingly random pictures that you're seeing in the screen. So before I do that, we need to create and establish a common vocabulary, a line of communication that we can understand each other better. And if there was such a line of communication, if there was such a dictionary, if you will, the first word in that dictionary would be optimization. So what is optimization really? So this is the definition of optimization: an act, process, methodology of making something such as a design, system, or decision as fully perfect, functional, or effective as possible. You see, now that definition really annoys me, and by the end of this, hopefully it should annoy you too. Why? Because the term perfect is a subjective term. And in optimization and mathematics, there is nothing we hate more than being subjective. So the first task, if you're asked to do any optimization, is to sort of define explicitly what is it that you want through a mathematical formulation, function, hence the name objective function. So basically this describes what is it that you want. Then you need to define that process, design, that setup that you were talking about through a set of mathematical formulation. These are called simulations. These can be as detailed or as abstract as you want it to be. Depending on what you want, it can be a data-driven model, it can be a conceptual model, what have you. So you know what you want, you know how it works. The idea is to find a way to leverage this to get better performance, because after all, if you can't change the performance of that setup, what's the point of optimizing it? That device that allows you to change and leverage this performance is called decision variables. Decision variables mathematically can be described as an array, as a vector. Each element in this vector is something that you can play with and get and change the performance of your system. So the whole point behind optimization or your optimizer is to go through all possible combinations, your search space, to find a combination that gives you a better result. Now, your search space may be limited due to some constraint or boundaries. Say you have limited resources, there are some legal or physical constraints that you have to account for, then you have some limitation and constraints. But the whole point is to find this area. Cool. For a long time, the first generation of optimizers, the only option we had at the time, relied heavily and perhaps solely on derivative of the functions. And we are mostly familiar with this. We have played around with these concepts in our high school, middle school, and we know how they work. And we also know the problem with them. The moment that you introduce derivative of a function, things become really difficult. The moment that you introduce new decision variables, the number of decision variables try to change into discrete, continuous, and you have mix and match situation, it becomes exceedingly hard, if not downright impossible to calculate the derivative of the function. So the next generation of optimizers try to address this issue. The way they did it was through a set of ideas that we're going to talk about. But the main concept was there was this instruction, a set of instruction that you can follow step by step until you reach what could potentially be your ultimate solution. Now, these solutions still, this set of next generation of optimizers still rely at least partially on partial differentiation, and or at least they have some assumption about the objective function. But still, they were a step toward the right direction. Now, the way they worked was they understood the idea behind sampling. So rather than looking at the whole objective function, the idea was to say, let's take some samples, look at that data, and try to abstract some information. This is something that we grew to use in different disciplines. Say, if you work with uncertainty, you know that if things get really complicated, you can use, say, Markov chain Monte Carlo as a way of generating the results and trying to analyze the output rather than trying to do the math and calculation behind it. The next idea was to use algorithmic structure. The idea is that rather than just being creative and trying to find a solution that is specifically tailored for your problem, what you can do is have an instruction. You can follow that instruction step by step. At each given point, the algorithm would tell you what you need to do and what is your next step and how you got there. And then eventually it should lead you to the solution. Now, this is very important because it allows us to translate whatever we have into computers. Later on, when we decide to translate this stuff to computers, it would become exceedingly easy. And finally, we started to appreciate and learn the art of compromise. You see, the first generation of optimizers were really precise. They knew exactly what the solution was, and that solution was exact. But the problem was that simulator of ours was an approximation itself. So whatever we were using was not necessarily a reflection of the real world. We were doing some approximation. So what's the point of getting an exact solution for something that is itself an approximation? So we started to learn that, okay, if we don't need the exact solution, what we can do is sort of use an approximation and get a near solution. And so long as this method gets us there faster, easier, we're fine with it. But there is still one problem. Even this second generation still relied on derivative of the functions. So how can we get rid of the derivatives? In order to do that, you need to understand the concept of direct search. The premise of a direct search is, I'm going to give you an example, and from this point onward, I'm going to refer back to this example throughout the presentation. So imagine you're in a landscape, and you know that there are some precious metals deposits within and underlying the ground. And the way that you can find this is through this metal detector, that device that you have. And every time you get near that device starts to making some noise, making some beeps. The louder the noise, the closer you are to that source. So the idea is, rather than listening to the changes in the noise with respect to the direction that I'm taking, the derivative of that function. We can simply listen to the noise for the sake of listening to the noise. So the noise is going to be a way to detecting how the points are doing. So in a way, you're evaluating these results and each given point within that space. And the idea is to use this noise, this evaluation, this information as a guide to move yourself toward the best point in that space. Okay, and the premise of the third generation of optimizers is to use that three principles that we saw earlier, and the idea of a guided search, the direct search, to create this third and final generation of optimizers. So this generation has assumed a lot of names ranging from meta-heuristic optimization. Some branches of it have been called evolutionary optimization, swarm intelligence, but the name that I prefer, and hopefully by the end of this, I can convince you that this is a more sensible name, is computational intelligence or CI-based optimization for sure. Now, this is by no means an exclusive or complete and thorough timeline, but this is some of the most important milestone in the history of the third generation of optimizers. And you can see here, say, pattern search, genetic algorithm, and PSO, some of the most known algorithm, and arguably one of the earliest inspiration behind this generation. Now, I want you to look at this graph because there is a pattern here, a very important pattern. And the pattern is, you can see earlier on, you only have a few new algorithms, new novel algorithms each decade. But it seems that in the last couple of years, it becomes more prevalent to come up with new ideas, novel ideas. Now, this is very important because in our line of work, having novel ideas actually has a meaning. The idea is that we have an unprecedented idea that actually works. Now, whether that's a legitimate claim or not, we're going to talk about that. But you may think, okay, but it makes sense. In the 60s, we didn't know that this idea is going to work. So once we started to appreciate this idea is working, maybe people will start to leaning more toward this idea. And more importantly, as the name of this generation suggests, these rely heavily on computation. So even until 1990s, the computers that we have was not able to fully take advantage of this idea. So once we have these computers, maybe that's the reason that we are seeing this many algorithms. Maybe, we're going to see. But before we get there, we have to understand how these ideas, how these algorithms actually work. We have to have some sense of how the instruction, how architecture of these algorithms work. So for the sake of argument, let's assume a 2D space. What does a 2D space mean? It means we only have two decision variables. Obviously, in most practical cases, we have more than two decision variables. Now, the color map that you're seeing here, representing the value of an objective function. Now, we want to minimize this, meaning that we want the colors, we want the points that are closer to the light blue. Obviously, if you're trying to solve the problem, you don't have this map. You don't see the values. That's the whole premise of this. Because if you see, you can easily spot that this is the best spot, right? So if you're trying to solve things, it's a blank canvas. I'm just showing you as a way to understand what is happening. Cool. So how does these algorithms work? So the idea was that we're going to use the direct search, meaning that we are going to evaluate a point and understand its function, right? Its value, how important it is to us. So these algorithms needs a mechanic that allows them to evaluate, and allows you to abstract information. So they deploy something called search agents. These search agents are simply something that an algorithm deploy to get information. Some algorithms use one agent, some use multiple agents. Now, as it is becoming easier to use parallel computation power are becoming cheaper and easier to access, we are leaning more toward multiple agent algorithms, multiple agent structures. But there are some algorithms, say, pattern search or simulated annealing, that still rely on single agent. In either case, the algorithm deploys these agents, evaluate their results. And each time it does, it gives you two sets of information. First, you would understand whether that point is feasible or not. By that I mean simply, does it hold every constraint that we have or not? We don't want infeasible solutions. If you can't hold the constraints, there is no point in having these results. The other thing is the value, the objective function value of that point. So we can get that information. Now, through a set of instruction, the algorithm would relocate and move that point to a new position. And how it does it is something that we will circle back to. But once you do that, you get to a new point. Now, the algorithm repeats this process, relocating and reevaluating that point until a termination point is met. At that point, the algorithm stops the search and returns the best solution that it encountered through its search process. Okay, if you want to formalize this process, this is the stages that we have. So at first, we initiate the search, meaning that we deploy the agents through the search space that we have. Again, we can have single agent, we can have multiple agents. That placement process can be deterministic, can be stochastic. Most of the time it's stochastic, but in either case, there are different ways to do that. But the thing is, after you deploy that agents through the search space, you need to start the stage. And the idea is that you need to preserve two policies. First, you want to explore that search space as thoroughly as you can. That makes sense. You want to make sure that there is no stone unturned. You want to make sure that you've searched that space as thoroughly as you can. But once you do find potentially good spots, you want to exploit that. You want to make sure that you pay more attention to the more promising regions. But you can't do this search forever and ever, right? At some point, you need to terminate that search. This is where termination stage comes into play. So how I'm going to terminate that stage? First, you may say, okay, I'm going to use time. Say, I'm going to search for 2 hours, and after that, I'm going to terminate the process. Well, you would see that that's not necessarily the most smartest idea that you can have. But there are other ways. Say you can limit the number of iterations that you have, or some algorithms, say simulated annealing and pattern search, they have a module embedded in them that allows them to sort of terminate their process based on internal metrics that they have. But in either case, you need the termination process. But let's see what is actually happening if you want to see these algorithms in practice. Let's go back to the example I was giving. So you were asked to find the most important, most valuable deposit in that landscape. So you may have enough money to be able to hire other people. You have a strong computer, you can deploy multiple search agents. So you know that your device has only 2 hours of battery. So you may be smart about your search process. You may say, okay, let's divide and explore every angle in that search space for the first hour or so. Once we are done with that, we can identify the more promising regions, the regions that gives us louder noise. Let's focus on these specific regions. So the way I'm trying to explore this idea is that initially you want to lean more toward the exploration phase and gradually move toward exploitation as your search is progressing. Now, is it always the case? Is it always the strategy that these algorithms use? Not necessarily. Some claim that I can do both phases at the same time simultaneously. Whether that's a legitimate idea or not, well, we're going to talk about this, but at least this is some of the algorithm's idea behind how they can do and conduct this search. And finally, if you've done your job correctly, the idea is that all of your friends and you should be gathered toward the most promising region. Cool. Now, here's the problem. Imagine initially you find this spot in the white circle in that region. Again, bear in mind, you don't see this map. You simply know that the points that I find is simply better than the points in its vicinity. This is the feature of this point, right? That's why it's called a local optima. It is doing better than every point in its vicinity. And if you look at it, it makes sense. But there is a difference. So we have a couple of local optima in this graph, but this one is a global optima in the sense that this is doing better than every point within that space. And the problem is, with these algorithms, there is no, if you don't have enough exploration properties, there is no way that you know if you're here or if you're there. Because you simply look at the points in your surrounding and you say, okay, it seems that I'm in a good spot, I'm going to terminate the search. But in reality, you're being trapped in a local optimum. Now, you may have a good exploration property. You may be able to get out of this spot and move toward that white triangle. Again, note that you don't see what is happening throughout the search. What you have is the information that you stored. You know that the points that you've encountered thus far was worse than this. And at that point, say you may have done the search for 3 hours and you say, okay, it seems that I'm in a good spot. This point is doing better than the points that I've seen thus far. So I'm going to call it a day and I'm going to return this as the optimal solution. But the thing is, this is better than most of the points that you see. It's not necessarily the global optimum. It's a near optimum solution. And this is something that we talked about, even in the second generation. If you're close enough, you're fine with it. So if you have a good exploitation property, the idea is the algorithm should direct you toward that white cross. But if you don't, you would be stuck somewhere around here. And again, to some extent, it is okay with us. But the real question is, how do you know you're in that white circle, white cross, white triangle, or for that matter, any point within that space? How do you know where you are in that search space during your search? Because all you have is the values that you're observing, nothing else. You don't see that map. And the real answer is you can't. There is no guarantee. No matter what you do, you can never be sure where you are in your search space. And data scientists are, for the lack of a better word, they're really chill guys. They're okay with this. So long as they minimize the risk, they're okay. Most of the time they say, okay, I've done everything that I could. This is the best solution that I can come up with. We have this in machine learning, data science, every part of the data science, we sort of see this behavior. But how can we minimize that risk? How can we make sure that at least we are doing our best to get close as possible to that solution? This is where you need to fine-tune set up your parameters, set up your algorithms to make sure that it's working the best for your specific problem. Now, how does it work? Well, you know that your optimizer is trying to search that simulator and to get the best result. Now, this algorithm has certain properties, exploration and exploitation, right? Now, the thing is that exploration and exploitation properties, that features may be good for one search space, but might not necessarily be the best option for other benchmark problems. So you need to be able to play around with these properties to make sure that it's worked for your specific problem, right? And this is where parameters comes into play. Majority of these algorithms have something embedded in them that allows you as a user to play around with these properties. Oftentimes, they're not called exploration and exploitation parameters, but you have to figure this out for yourself. But you can play around with these parameters, get different properties, get different features for your algorithm, and make sure that it's working for your simulator or your specific benchmark problem. Now, how do I know that parameter is working? How do I know that this is a good setting? So if you're doing an optimization and minimization problem specifically, this is a graph that you would see usually. The idea is to keep track of the solutions that has been returned in each iteration. And if you plotted it against certain metric that we're going to talk about, you should be seeing something like this. Know that essentially these are showing the same graph. It's different algorithms with different strategies, pretty much the same thing, but different strategies. And we're going to talk about how you can sort of switch between these two. But at this point, it's simply enough to know that these are essentially showing the same thing. So if you look at the tail of this graph, it's essentially telling you that, okay, as the search is progressing, the algorithm is not capable of finding better solutions. In other words, the algorithm is converging. Now, you may wonder, okay, if the algorithm is converging, this this might be showing that this is the ultimate solution, right? Well, not really. Convergence doesn't mean that the solution emerged from the search is the optimum setup. It simply implies that whatever you were able to find was the best. It's less likely to find a better solution for that parameter setting, for that specific algorithm, for that specific benchmark problem. So there are a lot of things here. It's less likely, meaning that eventually it could happen. There are millions and billions of other parameter settings, infinite number of other parameter settings that you can check. And more importantly, this is specifically for that benchmark problem. For a different problem, you may be dealing with something else. So essentially, what I'm trying to say is you can't be sure if you find the ultimate solution or not. You just have some sort of a guarantee, some sort of a sense whether you were there or not. But we talked about also how we can keep track of this progress. We talk about the metric of time. But you see, time might not be the best option because say if I use the same code for a different setup on a different system, which is more powerful, obviously it would progress more. So it might not be a way to compare things because everybody have a different setup. I might be a better coder, so I might write the code more efficiently and so on and so forth. So it doesn't make sense to use time. You may say, okay, let's do iteration. Iteration doesn't matter if you use it in my system or any other system. Iteration might be a good option. It's a step toward the right direction, but we're not still there. Why? Because you would soon realize that the bottleneck for your computational power and computational time is not the progress that is happening in the algorithm. It is the number of time you're doing the evaluation. That's the bottleneck of your computational time. So what's the problem? Well, some algorithms may be smart about this. They may use multiple agents at each given try, in each given iteration, but some may use one. So it's not fair to compare these two. So the best option is to use NFE, the number of time you evaluate that function, as a way to keep track of this. In either case, I talked about the idea that you can play around with the parameters. You can ensemble some modules on top of your algorithms to sort of swap between these two properties and add other things. If you're interested in these sort of subjects, this might be a good resource for you. But in either case, we answered most of the questions thus far. The only one perhaps crucial question is, okay, how's the algorithm is going to relocate and replace these search agents within the search space? How can we do that? Well, the idea is to be intelligent about this, to be smart about this, because if we just randomly place different agents and try to sort of relocate them through the search space, that might not be the best option. So we want to be smart about our computational time. That's why the name computational intelligence makes sense. So through the course of the history of this third generation, the idea was, the common practice was, I can't come up with a new intelligent idea. So I'm trying to imitate intelligent things. If I'm good at imitating intelligent things, trying to extract abstract version of that intelligence and try to incorporate that within my algorithm, that might work. That's the precedent. So you may look at the evolution process and come up with GA, differential evolution, and so on and so forth. Everybody look at something and try to come up with a novel idea. Now, you may ask yourself at this point, okay, I've seen a lot of new algorithms. You show me a lot of new algorithms. And we have, say, if that's the case, meaning that if you have these new algorithms, are they actually better than the ones that we've seen earlier? Are they better than the GA, PSO? If so, why do people still use GA? Why do people still use PSO? If that's not the case, meaning that the new algorithms are not as good, why are we accepting these new algorithms? Why are people trying to come up with new ideas? And the answer to that is based on a theorem called no free lunch theorem. And that's a very good principle and known principle in data science, which can be applied in our day-to-day life as well. So in essence, the idea is nothing is given to you for free. You have to pay the price for everything. You have to face the consequences. So in terms of optimization, there is no universal, definitive best optimization algorithm out there. Alternative, and more importantly, for each parameter, for each algorithm, you need to fine tune the parameters to make sure that that specific parameter setting is working for your specific benchmark problem. So you need to play around with this. There is no way around this. Now, I'm going to digress for a little bit. How many of you are working on engineering departments? Most of you. So a while back, I had this thought about the idea of no free lunch theory. If you're looking at a paper, you're reading a paper, the majority of researchers either explicitly or sometimes try to imply that, okay, the framework, this technology that I'm creating is the ultimate solution. Everybody else is stupid. The only thing that works is my work, and everything else is pointless. See, if you look at this theorem and try to understand it correctly, you will see that this is a wrong way of looking at research in general. So in the context of water engineering, I was trying to create this thought experiment and trying to explore whether that's the case or not. So I was able to find case studies that used solutions that on paper should have worked, but they failed in specific case studies. On the other hand, we would find solutions that shouldn't have worked, but they work for specific case studies. Again, the idea is there is no universal solution. If you're talking about desalination, what have you, they're working, but for specific problems. So you can find the ultimate solution in your field of research. Again, this can be applied in this. Cool. And again, that was a paper that you can read it if you have any experience. Cool. Now this is the fun part. Let's see if I can share the code. Now, can everybody see the code on the Zoom?
Yeah.
Awesome. Now, so you may wonder, okay, we have a lot of these algorithms. Let's see how they work. And in order to do that, I have this code which you can forward from my GitHub. At some point, you probably need to pip install some of other libraries, but it's going to be fine. If you have any questions, you can reach me. But you're seeing what is happening here is essentially we're going to have this drop-down window that gives you different benchmark problems. And there is this mysterious algorithm behind this, which I'm not going to name now, but you can use that to try to fix that problem and solve that problem. Now, the only thing that I let you play with is the population size and the number of iterations. Population size simply refers to the number of agents that I'm using at each iteration. And iteration is, well, as it says, it's the number of iterations I know. Now, if I play around with this, you can sort of see that the algorithm is convergent, right? We can all agree that the algorithm is convergent, right? Yeah. Cool. Now, this might not be as glamorous as we want it to be, so we're going to move on to the next goal. Now, we're going to see what is happening behind that search space. Now, obviously, I had to stick with 2D space because otherwise, how are you going to see that? But the idea is we're going to have different problems. And after the algorithm is solving that problem, you're going to see something like this. That red cross is the solution that the algorithm found at the end of the search. And this is the whole search space. So it seems that the algorithm was able to find the optimum solution, even if I don't necessarily give it a lot of power, computation power. We can all agree with that, right? Okay. That seems to be contradicting whatever I was saying to this point, because I didn't play around with the parameters. It was able to solve a lot of questions. So what's the point? Have I found an algorithm that was able to solve every bit of problem that I have without the need of fine-tuning it? If that's the case, then what's the whole point behind the things that I was saying? Now, let's do a bit of a quick survey. How many of you, and let's make it easy. Let's say that every algorithm that we have before 2000, let's lump it up together and say this is the old algorithm, say GA, PSO, and so on and so forth. Actually, PSO might be based on that. So I give you 2005 and before that. And anything after 2005 is a new algorithm. So we have the new algorithms against the old algorithms. And now the question is, this seemingly mysterious algorithm that is working really well, do you think it's an old algorithm or a new one? With a show of hand, how many of you think it's an old algorithm? Meaning, say, GA and older algorithms are working really well. So how about the new ones? Okay, few people, most people even didn't show up. But this one. Let's assume that most of you said the old algorithm. In that case, I have to tell you that the majority of people in this room are wrong. But to be fair, everybody is wrong. Because technically, I didn't use an algorithm here. What I did was use a pseudo algorithm. What I did was simply generate a random set of solutions, try to put it in a pool, preserve the good ones, toss everything aside, the bad ones aside, generate new ones, and try that process for a number of times, and call it a day. It wasn't intelligent. I didn't do anything intelligent, yet, surprisingly, for every problem I gave it, it was able to solve the solution. So there is something interesting here happening behind these algorithms. I was able to generate something smart without being smart. Now we're getting somewhere. We're trying to figure out what it's. Can everybody see the slides now? Yeah. Cool. So what is happening? Assume that you're asked to find the optimum solution in that search space, that golden rectangle. Square? Is it square? Yeah. And the optimum solution is the center of this white circle. Now, the smaller the circle, the more closer that you're finding that getting to that optimum solution. Now, mathematically speaking, placing a random point within that circle, and obviously it doesn't matter where that circle is, the mathematics is all the same. The probability of finding a point within that circle is always going to be something. Obviously, it's going to be smaller. The smaller that circle, the smaller this probability. But still, my point is, there is still a probability. And I'm being slightly, even if I'm slightly intelligent about selecting this point, say in each iteration, if I get closer and get better results, I try to move that generation process closer to that spot. So it becomes exceedingly easier to find a solution without demonstrating any sort of intelligence. And my point is, okay, so I'm using brute force rather than intelligence. But that was the premise of these algorithms. They claim that they are going to be intelligent. Now, whether they are intelligent or not, whether they're using brute force or intelligent, we don't know. Why? After all these years, we don't know what we're doing? Because we don't ask questions. We stopped asking questions. We started to accept the results because of the results. The algorithm is working, giving you good results. Okay, I'm going to call it a day. I'm going to publish that bit. Because the algorithm is seemingly working, why should I ask the questions? And this is the source of the problem. Now I'm going to go on a rant for at least 10 minutes, and I've been waiting for this for a long time because that's the whole point behind this demonstration. So if you missed all the things that I've just said, it's fine. This is the most important part. And I'm going to talk generally about computational intelligence, artificial intelligence, because that's something really important. There's something wrong happening in our very eyes, in front of us, and nobody's seeming to pay attention. Before I do that, I'm going to tell you an anecdote. So a while back, I was invited or attending a conference about computational intelligence. In that conference symposium, everybody from people who were working in governments or some of the largest companies in the world was present. And they were trying to talk about artificial intelligence, computational intelligence, and obviously the name of ChatGPT and the natural language processing models came up. And somebody who is working at arguably one of the greatest companies in the world. And by the way, he was working in the industry. It wasn't just a random person. He started to make this claim. So that ChatGPT or what have you was given a series of questions that we usually give it to our high school students. And now ChatGPT was able to solve that question better than 95% of the students. And he was trying to imply that based on this statistic alone, we are getting and reaching to that AGI, to that era that computers are doing everything and everything is now solvable through ChatGPT. But see, that was really annoying and really stupid, if you ask me. And I was really annoyed until I talked to someone from the US government. She was working in an office about data science or something like that. And after I had that talk, I sort of felt a bit more comfortable and more at ease, because at least I was assured that at least she understands what is happening. She understands that's a bogus claim. So the point is, and Ramiz and Milad are going to talk about this, but if you have a machine learning and you have that training data set, if you train your model based on that data set, what would happen if you ask a question based on that training data set? It would obviously generate a good result. So if you have an NLP, natural language processing model, that is, and you're trying to ask it a question that you gave it in your training data set, obviously it's going to generate a good result, but it doesn't mean that it's smart. Am I undermining the importance of ChatGPT? By no means, but I'm saying at least understand the scope of things, because a lot of bad things are happening. See, back in the days, even now, if you tell someone, okay, this is a website, and there are a lot of claims and information in that, most people, well, I know I'm being a bit generous when I say most people, but at least some people would be a bit skeptical about the information that they're reading on that website. Now, here's the tricky part. If I train a natural language processing model based on that data set that you would see in that website, and give you the keys to play around with that model, and that model starts generating the result, you would automatically give it credibility, because this is not a website anymore, this is AI. And the moment that it's AI, everybody thinks that it's the best thing solution out there. You don't ask questions, you don't understand what that data set, that information is coming from. Now, the other problem is some company decided at some point, I'm going to launch and do this experiment on a global scale. Nobody asked the question. Nobody asked why this company is doing this, where this information is going, what happens if the model becomes really intelligent, and so many other questions. I'm not saying that they have malicious reasons behind their act, but it's irrelevant. What if the next person does? You open the door. Now everybody can launch these models, and everybody do. Who is going to regulate this? And more importantly, even if you regulate it, is regulation the answer? Perhaps not, because a lot of things we're trying to regulate it and it didn't work because public didn't understand. And more importantly, we are the final line of defense. And we have to start acting now, because everybody else seemingly is giving up in this battle. I know that people are worried about computers becoming exceedingly smart, AGI, and it's fine. You can think about this. I don't think we're even close to that, or we may ever get there, but there are more important battles that we need to fight. And nobody is seeming to care about this. We have to start asking the questions. At some point in time, we all gave up. We start asking the questions. We stop doing our job. As researchers, we should do that. We should start asking questions. We should try to understand, okay, you're telling me that model is working. Why? You're treating them as black box, whether it's for optimization, whether it's for machine learning. We just accept the solutions as are because they are good solutions. We don't understand what is happening, and that's wrong, because what if there is some miscalculation behind that, and it's giving us good result to some point, at some point it would fail. We saw that in ChatGPT and many other things. When we're playing Go, when we're playing chess, we understood that they're not understanding logic, and yet we're relying everything on them working the way they should. And that's the danger. At any point, if you're interested in learning about artificial intelligence in the context of how they can be used for different optimization algorithms, this might be a good book for you. I know it's a self-promotion. It's going to come out around October. And if you want to stay in touch with me and our team to talk about research ideas, or simply start to chat about these topics, we're more than glad to have a talk with you. And these are the ways that you can get in touch with us. Thank you so much. Awesome. So if anybody has questions, we can do it now, or I'm going to be solving. We're going to have some refreshment. Sure.
Can you please share the PPT?
Definitely. I'm going to upload it in my website. I always do. So it's one of the ways that you can get it. Just simply go to my website in a couple of days and do that. Cool. Hello.
Yeah, hi. I would argue that brute force is an algorithm.
Yeah.
You know, it is some kind of intelligence, just very robust.
Okay.
You know, just very simple,
Mhm.
and quite bold as well.
Mhm.
So I would argue that most of the people were not wrong.
But see, the thing is,
It's
brute
an
force,
algorithm.
it's an algorithm, but the claim of intelligent is something else. It's one thing to explore everything and put everything in resources that you have to search everything. Yes, it's going to give you good results. But the premise of this was I'm going to randomly, I'm not going to use all your resources. I'm going to be smart about searching, allocating my resources. And it's simply what is happening. They claim that they're intelligent, but they're using brute force. I'm not saying brute force is bad. I'm saying if you're using brute force, be front about it. I'm using brute force. But they claim the idea, they attach the label of AI, computational intelligence. They claim that they're more efficient than brute force. But in reality, now I'm working on a lot of papers in parallel about this very same concept. I'm going to break down algorithms and see how many of them are actually using brute force, or they're being actually smart about this. And you would be surprised, a lot of algorithms that you would check, they claim that they're smart, brute force is doing better than them. Random search is doing better than them. That's really strange. You have a random algorithm, the one that I was showing you, and the smart, intelligent algorithm that was published and claimed that you be the best algorithm out there, they were not able to solve that problem. Because I changed the problem. See, the trick is if you know what you're doing, you create a setup that allows you to master problems. They use benchmarks that allow them to mask that problem.
Well, obviously, if it's optimized on the benchmark,
Yeah.
it's a bit like cheating.
See, the thing is, even that I would be okay with. But if you deliberately choose a benchmark that you know that it's going to work with your algorithm, doesn't show your flaws, that's cheating.
I mean, your algorithm should not be tuned to a benchmark.
So the idea is, as I mentioned, your algorithm should be able to solve every problem, including benchmarks. So benchmarks are a way of demonstrating, okay, this is a working idea, it works, right? And you can say that about anything. At the end of the day, whether it's a mathematical benchmark, engineering benchmark, you have to showcase that your algorithm is working. But my problem is there are mathematical ways to choose benchmarks that work for your algorithm, but they sort of mask the problems within the inherent problems with your algorithm. That's the problem. So,
I
yeah.
have another question.
Sure.
You mentioned Monte Carlo Markov chains. Do you think you can fall into local minima as well with Monte Carlo Markov chain? Or you have the same issues as with like
everything. If you're not careful, that was my general point. Everything that we attach to the label of data-driven models, you can cheat your way out of that. If you're not careful, if you know way better than what you should know about how the algorithm works, you can cheat your way around it. So we have to, and my point is, you don't know why this problem is happening. At this point, we have thousands of new algorithms, we have different names for them, but we don't know why they're working. So my point is, okay, rather than coming up with new algorithms, let's break them down to their components. Let's understand what they do. Let's isolate that behavior. Let's see what it does. So if there is a false behavior, let's try to fix it. Rather than coming up with new algorithms every day and trying to claim that I'm the best scientist out. Anyway, just thank you for your questions.
If I can say something, I mean, very, very general comment.
Yeah.
The thing is, is the old issue we always had between interpolation and extrapolation. In a way, we are confident when we are exploring a domain. We're getting some responses, and we can sort of get the sort of expected response in the domain. Anytime you go out beyond that domain, it's more an act of faith in a way. So I think that the issue is that between intelligence and infallibility. Intelligence doesn't mean to be infallible. We can get mistakes even if we act in a very intelligent and smart way. And here we are way beyond that. So basically, once I was speaking with a colleague in computer science, I said to me, machine learning is basically like a intern on steroids. Basically, you can ask whatever you can ask for an intern to do. Artificial intelligence will do it, but it's basically based on things that they know. And as you said, if we fed it with like wrong information, inaccurate information, it comes out with inaccurate results. So we are way beyond the intelligence in some cases, and even that intelligence is way beyond infallibility. But the risk that I can see is that people are now, relying on the infallibility of artificial intelligence, which is the danger, I believe.
Exactly, spot on. Because I agree with everything that you said. My only sort of thing to complete this argument is, yes, we understand that. At least some of us understand that we shouldn't rely on them solely because they are AI. We should understand that there are some limits. But what are the limits? We know one of them, for instance, if you're within the boundaries that we explored earlier, should get good results. Even that's questionable. But what are the other limits? Are we exploring that? Because in the previous generation of models that we were using, we were asking the questions. Nowadays, we're simply saying, okay, and data scientists are usually so lazy to answer any questions, so they just tell them, okay, this is it. And they say, okay, this is the result. It's working. This is the value that you wanted, right? R2 is, say, 85%. So my model is working. Don't ask me questions. You don't ask why it's not working.
Is it possible that it's also because the complexity of the system evolved to a certain point that the developers are relying on previous models, which are black box, which internalize to black box, which internalize to black box, and basically we are sort of nesting in a number of things that we have.
Maybe, and also maybe it's not necessarily that complex. We like to pretend that they are, but if you look at it, it's just simple mathematics. It's just, this is the weight of this cell, this is the weight of this cell, I'm going to add this to get to this next cell. That's pretty much it, right? But we like to pretend that this is way beyond our understanding, so I'm not going to try to understand it. It's so complex, I'm not going to touch it. But we can isolate things and try to understand in simple cases and then try to extrapolate into bigger problems. Cool. Okay, I think with that out of the way, we can sort of stop now, take a little break for how long do we have? 30, 45 minutes?
Something around that.
Yeah, okay. And then come back and definitely join us back if you're online for the next session, which is going to be really awesome. We have machine learning, data mining, and all that jazz. Cool. Thanks, everybody.
I just want to